So now we've gone through the statement of the alternating series test and a little bit of some intuition behind it. And I want to go back and look at some examples where we can actually apply the test. So these examples are actually the same ones that we used as just giving examples of alternating series. And now I want to decide, do these alternating series converge or diverge? So one thing that's nice about the alternating series test is it's typically pretty clear when you want to use it. It's when you have an alternating series. And so here I see that I have an alternating series, and I need to check then two things. So in this case, the b sub k that our theorem talks about, remember we said b sub k is always just the absolute value of your term. So in this case, it's just going to be 1 over k. So I need to check, first of all, that the limit of 1 over k as k approaches infinity is 0. There's not really a lot of work to show here, so kind of writing it down suffices as me indicating what I'm looking for. And the other thing we need is that b sub k plus 1 is smaller than b sub k. Well, b sub k plus 1 is 1 over k plus 1, and that is in fact smaller than 1 over k. So both of these conditions hold, and like I said, not a lot of work to show here, but we can say that then the series converges. And again, I want to justify by saying that this is by the alternating series test. So this is one kind of classic example of how we could show that an alternating series converges using the test. This next one is a more complicated series. Again, I want to point out it is alternating, and b sub k, which is the absolute value of my terms, is the square root of k over k plus 4. So I first want to check and see if the limit as k approaches infinity of root k over k plus 4 is in fact 0. And again, you can see here I have k to the 1/2 in the numerator, k to the first power in the denominator. This is going to be true. The second condition would mean to check that the square root of k plus 1 divided by k plus 1 plus 4, we would want to check that that's smaller than the square root of k over k plus 4. So this is not so obvious because we can see that both the numerator and the denominator on the left are larger. So if it's not immediately clear, so I'll say in the last example, the numerator was the same, but the denominator was larger on the left. So if it's not obvious, you have to do a little bit of work to actually show that this is true. So first of all, I'm going to observe that this is just k plus 5. One thing that's making this difficult is the radical. So one thing I can do, both sides are positive. So we can square both sides. So k plus 1 over k plus 5 squared. We want that to be smaller than k over k plus 4 squared. And again, maybe I'll write this out. This is k squared plus 10k plus 25. And this is k squared plus 8k plus 16. And having, again, k on top and bottom is making it hard to compare this, so we could then cross multiply and check that k plus 1 times k squared plus 8k plus 16. We want to see, is that smaller than k times k squared plus 10k plus 25? So we no longer have this rational expression. So if I were to multiply this left-hand side out, we'd really be seeing is k cubed plus 8k squared plus 16k plus k squared plus 8k plus 16. Is that smaller than k cubed plus 10k squared plus 25k? So one thing we can do is start to cancel like terms. So k cubed, I have 10k squared on the right, and together I have 9k squared on the left. So if we subtract 9k squared from both sides, that will leave 1 on this side. Likewise, if I join the 16k and the 8k, that's 24k. If we subtract that from both sides, that will leave 1k over here. And then the only thing left on the left side is 16. So if this inequality is true, then the one we started with is as well. this is a little bit easier to check. And in particular, I'll point out that this inequality is true as long as k is 4 or greater. So if you plug in 1, you plug in 2, you plug in 3, you don't get something bigger than 16. But as soon as you plug in 4, you do. It turns out that this is good enough. So in the statement of the theorem, we said that we had to have the terms decreasing. What this is saying is that once I get to the 4th term, then my terms are all decreasing. If finitely many of them are not satisfying that they're decreasing, that's okay. And again, this is just as a little background. Why is that the case? Well, if I'm looking at the sum from 1 to infinity of some a sub k, we can write that as the sum of the first 3 terms and then tack that onto the sum from 4 to infinity. And if I know that this sum satisfies the conditions of the AST, converges, well, tacking on 3 finite terms to the beginning of it is not going to change that convergence. So I'll point out that this is good enough. And this is likewise true. If you could find out it was true for k equals 100 or more, that would be good enough as well. As long as there's some fixed point after which it's always true, then we've satisfied that condition. So now I see that both conditions of the alternating series test hold here. So again, I can say that the series converges by the alternating series test. So if it's not quite so clear that the conditions hold, you might have to do a little bit more work. That's what we're seeing there. And my third example I want to consider is, again, an alternating series. B sub k is the absolute value of a sub k, which would be k over k plus 3. Then if I want to check my conditions, first of all, we take the limit as k approaches infinity of k divided by k plus 3. And first of all, notice here that we don't get 0, we get 1. So unlike the previous examples, I immediately see that this first condition fails. I can't say that this series diverges by the test for divergence, or excuse me, by the alternating series test, because the way that the statement or the test was written was that if these conditions hold, then the series converges. There was no talk about what would happen if any of the conditions failed. However, we have just shown that the terms do not approach 0, this portion, but if the size of the terms doesn't approach 0, and then you start to think about the alternating version, those terms would then just oscillate, but again, away from 0. So if this condition ever fails when you're trying to use the alternating series test, you can say that the series diverges, but the reason is just not the alternating series test. Instead, you say the series diverges by the test for divergence. And so that's a subtle but important point about this theorem when you can show that the limit of the terms does not go to 0. So be a little bit careful with that. And the last thing I want to check is, what if you have an alternating series, but again, it's hard to kind of verify one of these conditions. So in this example, what we see here is, again, these are alternating terms. And it is true that the terms are approaching 0 as you go on, but the problem is that they don't have every other term decreasing. So you've got 1/4, and then we've got 1/8, I've got 1/9, and then I've got 1/27. So when you start to look at these terms, if we were to plot them, they're decreasing, but kind of in a stair-step manner. And so that's the idea, that we can't say that every other term is decreasing, although they are trending towards 0. I can't then say that both conditions of the alternating series test hold. So here we don't have that b sub k plus 1 is always smaller than b sub k. So instead, what we want to think about is, if I can't, then this is not a case for the test for divergence because these terms are approaching 0, but I can't use the alternating series test. Well, we can still try to work on whether or not this series converges, even in this case where AST doesn't apply. In particular, notice that you could focus on the squared terms, which seem to all be positive, separate from the cubed terms, which all seem to be negative. So in this pattern, we could write this instead as the positive sum from k equals 2 to infinity of 1 over k squared minus the sum from k equals 2 to infinity of 1 over k cubed, both of which converge. So this one converges and this one converges. So in that case, the difference converges. So this tells us that the series actually converges. And I didn't use the alternating series test to get there. So the other thing I want to kind of point out with this example is that we saw that one of the conditions failed from the alternating series test, but that didn't mean that the series diverged. We just had to look at it a different way. In this instance, break it into two p series. So that's kind of the connection here. A difference of p series that both are known to converge. And then in that case, that means that that difference also converges. But by the other token, we've also seen that you can have one of the conditions fail, like our last example, and the series diverges. So this, again, just kind of emphasizes the importance of not ever saying that the alternating series test allows us to come to a conclusion when one of the one of these conditions fails. We just have to look at the series in another way and potentially use a different test.